Okay, so I have my recording. Okay, so today hopefully we'll have a little bit of a shorter lecture. Our goal is to finish our data flow slides. Remember, we're doing data flow analysis of straight line code. So we just basically doing things which we could easily do just by intuition, by eyeballing the programs. But we're formalizing them using equations. We see how solving those equations gives us a solution. And then once we're comfortable with this, we move to programs which have control flow and have loops. And we'll see that the same equations work there too. And just solving them is a little bit more complicated because you have to iterate the solution process until you get to a fixed point rather than just doing one iteration. Last time we looked at available expressions data flow analysis. I'm going to repeat this again, just a little bit quicker, just so that we are on the same page. And then we're going to look at the copy propagation and reaching definition. So what do we need to do here? So we have a data flow analysis. That is, we want to compute a bunch of facts at different places in a program. And these facts depend on the flow of data through the program. So we always have a domain of facts, a data flow domain. In available expressions, this is, for example, the set of all expressions that the program computes. And what we want to know, that's our fact. And what we want to know at every statement of a program, which of those facts, which of those expressions happen to be computed and stored in some variable, and which aren't. The way we do it is we're going to construct the equations that will explain what happens at every statement. And that we're going to do by identifying the set of gen and kill sets, where gen sets would be all the sets that represent what the statement produces, the new, well, in this case, available expressions that are constructed by the statement. And kill represents all of the data flow fact that the statement invalidates. In this case, all of the expression that it makes unavailable. And once we have this for every statement, we string them together in a natural way. If one statement is executed before another one, then its output goes as an input into it. And then we just solve the system. There's no circular dependency in that system because the program is straight line. So the solving simply means propagating data flow facts from top to bottom until we have a solution for every point. This is our equations. These equations will always look the same. There's really two kinds of equations, forward, and so far we're only looking at forward analysis, and backward. Forward means that we're going to go from an order of execution, so that we're going to connect the in of one statement will be an output of another, and we're going to compute an output from in. So that's forward. Backward will be the opposite direction. We'll see it in a few lectures, but that's the only two equations you ever need. And then the equations always look in this way. So in order to understand them, it is good to have a mental picture of how the program looks like. This is this picture on the left. Each green box represents a statement, and each purple thing represents a quantity that we have in our equations. So one thing that we have is that for every statement, the in variable corresponding to it. So for example, look here at inf2. Yes, I'll pick a different color to point. Okay. So for example, we look at inf here, inf2 here. Well, it really depends on the out of the previous statement, which is out1. This is what this equation is saying, that in of any statement S depends on the output of its predecessor. Now, in our case, since we said it's straight line programs, this disappears because we only have one predecessor, so there's no intersection. But this is preparing us for the case when we're going to have a statement with multiple incoming flows. In which case we say, well, what's true at this statement is the intersection of everything that flows in it. So that's why we have the intersection. Okay, so this is the first equation. And then the second equation says, how do we compute an out from each in? And the idea is that what we do is we take the in, we remove from it everything that is no longer valid because the statement invalidates it. And then we add to it everything that the statement generates. And that's out. Should be pretty intuitive. Okay. So now let's go and look at our example. So here's the code that we want to analyze right here. And we want to compute the available expressions. And so we'll need to set up our equations. So we'll have, in one, out one, and then in two, out two, in three, out three, in four, out four. And we have to write, so this will be our variables, and then we'll have to connect them, well, the way we just saw in a previous slide. So let's go and do this. So in order to build our equations, we need to know what is the gen and kill sets for every statement. Now, this is the part that does depend on the particular analysis. That's going to be different for each analysis. Here we're doing available expressions. So what is generated by the statement? Well, each statement, because we're in a 3-address code, each statement generates one expression and kills any expression that contains the variable that is being assigned. So for example, the first statement kills anything that has t, generates x plus y. Second one kills anything that has a, generates t plus z. Kills everything that has u, generates x plus y. Kills everything that has b, generates u times z. Now, in order to actually build our gen and kill sets, we need to know what is the set of all expressions that can ever be available. That's easy. We just scan the program and we compute all of the expressions. So this is 1, 2, 3, 4. Happens to be just 4 expressions. It doesn't matter how big our program is. It doesn't matter how long it executes. It doesn't matter if it has loops or anything. The number of expressions in it will be finite. We just walk over its AST and collect all of the expressions. The gen sets are easy because this is just the right-hand side of every statement. The kill sets, we need to go and see out of all possible expressions, which are the ones that actually can be killed. So again, we go over here, say, kill everything that has t in it. We look at all expressions that are ever available. Oh, this one has t, so that goes into the kill set. We go for the second one. This one kills anything that contains a. There is no expressions here that have a in it, so the kill set is empty. This one kills everything that contains u. We look at all expressions to see which one has a u in it. This one does, so that goes into the kill set. Now, it's important that when we do this, we're not doing any additional thinking, right? Because remember, this is an example that is very simple. We're looking at a particular case, a straight line code where things are very, very simple, but we're trying to build an algorithm that doesn't actually depend on this. We're trying to build an algorithm that seems to be more general, that captures our intuition in here, and then we'll see that actually the same algorithm works for more complicated systems too. So this generation of gen and kill set, when I do it, I don't really look at the program. I don't see which statement follows which one. I don't see whether something will actually be used or not used in the program. I just do it completely mechanical, exactly as I described. So essentially, eventually, I would want to implement it. And then in that case, I don't want to look at a program and see what happens first, what happens second. I just want to generate those sets and give it to a data flow equation solver to solve. Okay. So again, this is really important because it's very easy if you're just looking at this, and it's very easy to get lost a little bit and use your intuition too much. So for example, here, why is u times that in a kill of 3? Right? If you look at this program, you'll see that u times that is computed after 3. And so it's not even in this program computed before. So it's not even really available before. And what's the point of putting it in a kill set? And that would be a bad way to think about it. You don't look at a program, you don't look at, why something would be useful or not useful. You do it completely mechanical. The mechanical steps say, this kills everything that has u in it. Look at all expressions that have u. Put this in here. Don't worry whether it's actually necessary or not in any, when you solve the data flow equations. It's just a mechanical thing to do. And this way, you don't have to worry where maybe there's another, say, execution flow. Maybe this whole code is actually in a loop, and whatever is computed here, u times that, it actually flows back in. And then you have to make sure that you're not mistakenly thinking that you can use it again here instead of recomputing it again. All right, let me pause for a second and see if there are any questions. I don't see any questions. So again, the reason why I'm stressing this so much is because that's a common place where people get confused. They look at the simple examples that we use to illustrate this, and they think they understand, but they understand more the example than the technique. And then when they ask to apply the same technique on a different example, then they discover that it's not necessarily as intuitive and get lost. And it's really important to separate here the intuition so that you understand what's going on from the mechanics of the actual data flow algorithm. All right, so next is solving. We have our equations. We just write them down and we start solving by Gaussian elimination. That is, we find a solution for one variable, we plug it into the equations where it appears. That has equations with less variables. We will create another equation where a variable just equals some value, and we keep plugging it in, plugging it in, plugging it in until we have a complete solution. So this is what we have here as our as our equations. So the structure is very simple. It's a linear program. So a structure is each in is an out of the previous one. There's no intersection, no connection. And then the equations for each statement are always the same. We compute an out from an in, and the indices are exactly the same. So out 3 is from in 3, out 4 is from in 4, and so on. We can see here, before we even plug all the gen and kill values, we'll see here, for example, that in 1 has a solution. In 1 is an empty set, which means we can plug it in here. We know kill 1 and gen 1, they were in the previous slide. We do this computation, and now out 1 is solved. It has a particular value, a set of facts. Then we plug out in here, and now inf2 has a solution. We take inf2 and we plug it in here, and now out2 has a solution, right? And so on and so on. That's Gaussian elimination. And because our program has no loops, and there's no cycles in the program, there's no cycles in the dependency of these equations. So the bigger number of a variable depends only on smaller variables. And so as you do this computation, you eventually solve everything. There's no loop back at any point. So here again, we're just doing the solution. So we recreate our gen and kill sets from previous slides. We plug them in. And after a while, we get this as a solution. And remember that whatever we do here by hand will always be quite simple. And so we should always be able to eyeball it and see whether the result actually makes intuitive sense. And if it doesn't, then there's probably some mistake in our computation. So what's our intuition? Well, the intuition is that in for each statement should be exactly expressions which are already computed and stored in some variable. And out should be expressions that can be used right after that statement. Right. So if we go, for example, to this line between 2 and 3, we know that x plus y is computed and still available. It's stored in t. And t plus z is computed and it's still available and it's an a. And if we look at out of 2 or in of 3, we expect to see exactly that. X plus y and t plus z. Right? And so same thing, we can go the other way. If we look at any one of those output sets and we can say, oh, why is this here? Well, we should be able to go back to the program, trace it back, find out where this expression is computed, and then see that, in fact, it hasn't been changed in any way. So for example, if we want to check why do we have x plus y in here, well, we see that x plus y is computed right before. It's stored in a variable u. U is not changed, so x plus y should be available at this point, and it is. Okay. So once we have our available expressions, now we can do our common subexpression elimination. What we will say is that if we come to a statement like the one here, and we want to compute an expression like the one here, but it so happens that this expression is already available on entry, that is, it's an expression that is already stored in some variable, then we can replace the expression by the variable that makes it available. Well, in this case, this will be t. Our computation is like this. So we said that all we have to do is take an intersection between what is available on input and what the statement actually wants to produce. And if there's something here which is not an empty set, then we know that we can use whatever is available instead of generating it. And so we can eliminate the common subexpression. Now, in this case, the analysis itself doesn't tell us how to do this. So it doesn't, the available expression analysis doesn't tell us in which variable the expression is available. But we can fix this up, for example, by keeping track of the source of an expression, or we can separately keep track for every expression where actually it's computed. Or we can first do this common subexpression elimination computation, find out this, and then do extra analysis to figure out, well, which variable do we get to use for that. Right? That's the difference between the data flow analysis and an optimization. The data flow analysis just gives you the core facts, and then when you build an optimizer, you figure out how you actually want to use this fact. Possibly you need some extra information for that. Yep. Any questions? Looks very quiet. No, maybe there are questions. So the question is, if I look at CSE, if I look at this computation, we only use insets and gensets. So why do we need outsets? I mean, maybe we don't even need to compute them. And the answer here is that you need the outsets in order to solve the equation. Right? Our equations have in and out. It so happens that when we formulated our common sub-expressions, we formulated them using only in and gen. Right? So you need to solve the equations. You don't need to know what the solutions for out is in order to compute common sub-expression elimination. But you need to know what out is in order to know what in is during the computation. Okay? So, I mean, that's, you should be common to you, and there's lots of places where in order to solve equation, you introduce intermediate variables. And then you don't necessarily need solutions to the intermediate variables in your final application of that equation, but you still need to know those intermediate results during the computation. All right, so this is CSE. So next, we're going to do copy propagation. And so what we need for copy propagation is we need to know where to propagate all the copies, right? So the problem was, maybe we should go back to this just to remind us where we are. I need my eraser. Right. So code is in 3 address form. We've done common sub-expression elimination. So now we don't have this computation of x plus y twice. But we don't like it because we have this variable t that's available at this point. And now we're also creating a variable u. And here we're using q, whereas we could have used t instead and make this variable unnecessary. And so we need an analysis to know at which point which variable equals which other one, so that we can propagate the copy, so that we can replace the use of a copy by the use of sort of the original source of that information. So, right, so here we are. So first of all, it's a data flow analysis. It's a forward data flow analysis. We're going according to the control flow, which means the equations will always be the same. Right? So it's still exactly the same equation. What changes is what is the set of data flow facts that we're propagating, and what is a gen and a kill in this particular context. So what we keeping track of is what are the copies. So which variables we have, which are copies of other variables. That's our set of data flow facts. So in is a set of copies we have before the statement. Out is a set of copies we have after the statement. Gen is the set of copies that the statement creates. So for example, a statement u equals t will create that copy, that u equals t. And kill is a set of copies which are killed. Right? And of course, if you assign a variable, then you basically kill all any copy information about that variable. Okay, so again, this is our code. This is the second step. What we'd like to find out in here is that this creates a copy, right? And then once we know that this is a copy, we will be able to figure out here that a copy u can be replaced by t. So we need our gen and kill sets. Okay, so here we have the only one copy being created, which is here. And so we have u as our copy. And because the variable u may be assigned multiple times, we need to separate which of them is a copy. So u is not always a copy of t. And so we're going to use a line number to indicate which particular assignment it is. So we know that at this point, at statement 3, we create a copy, which is a copy of something. We don't record what. We know from the program that this is of t. And because there could be multiple assignments of u, we remember that this is u on line 3. When we go to kill sets, we know that whenever we assign a variable that is part of a copy, we kill all the copies for that variable. So here we're assigning t, So a kill set will be any let me pick a good variable, any say w equals t. So all w's like this would be killed. So any copies that are created of t are killed because t is reassigned. And so we look through our program, we see only one statement that can create a copy, and this corresponds to u3 because that's a u at line 3, and that becomes our kill set. There is no kill set here, no kill set here, and no kill set here, because we only have one copy, which is u equals t, and the only way to kill this copy is to assign something to its right-hand side to t. So only an assignment to t is a kill. And we only have one gen, because the only way to create a copy is to assign a variable to a variable, and we only have one such statement, and the gen that we create is u3. Okay. Once we have this, we just need to solve our equations. But before we do so, let's look at a different example. Let's see. So we took a slightly different program. So where we reassigning t in here. So we had an extra assignment, t equals 7. Right? And so here we want to make sure that we don't mistakenly decide that u is a copy of t. Because of course it's not. U holds the old value of t, and this one has a new value. And so to make sure that this does not happen, this is where the kill set will be. So if we look at the kill set of 4, while we're reassigning t, so we need to scan the program for all copies where t is on the right-hand side, which is this one, and add all the left-hand sides into our kill. And because there could be multiple such things, we need to identify them by their location. So this would be u3. Right? And so this statement in line 4, it will kill a copy u3. So by the time we get here, u3 is not a copy, or it's not an available copy. And so then we cannot really replace it in this statement. But we're going to go back to our previous example. So again, we do want to get a copy propagation to appear in here. We get our equations. They are exactly the same as before. We write them out. Again, at this point, this, and this will look exactly the same as before. The difference is only that we know that the gen and kill sets are different, and the set of data flow facts are different. Now it's sets of copies, not sets of available expressions. To solve it, again, we just plug things in and simplify, plug and simplify, plug and simplify. So this is our gen set. This is again the equations. We plug them in and we get the following thing. So up to statement 4, up to here, there is no copies created. Up to here, up to in of 3. This is in of 3. There are no copies created because there is no statement that we execute, which is left-hand side, which is variable equals variable. Right after at in 4, we have one copy, u3. And then that copy survives the statement because the statement doesn't change anything that the copy depends on. So it doesn't set t. And so we have u3 is an available copy at out 3 and out 4. Okay. So now, in order to turn this analysis into optimization, well, all we do is we say, well, if there is something that is incoming into a statement, and it's actually used in the statement, then we can replace the used copy by the variable that it's a copy of. Right. So we look at this is an interesting one. What's used that for? And so what's used that for is u at line 3, and that which is from somewhere else. And we know that u at line 3 is an available copy at line 4. And so we can replace it by what it's a copy of. So we look it up in the program. It's a copy of t, and so we can replace it by t. Let's see if there's any questions. Okay, kill sets. Let's go to where they make sense. So what should be, okay, so first of all, what are the data flow facts? Right here. The data flow facts are var underscore I, where at line I, the statement is var equals var prime, where var prime is another variable. This is a set of data flow facts. This is sounds maybe once I start writing it, it looks very complicated, but it's really a simple thing. It's a set of data flow facts. All facts that we can ever have is you go through the program, you look for statements like this, where the right-hand side is a single variable, and then your data flow fact is this left-hand side with a number, which is what line you at. So for example, in this program, we only have one data flow fact that we can ever have, which is U3. So all of our sets will either be empty sets or sets containing U3, nothing else. On the other hand, if I take this program, then let me get rid of it. Okay. If I have this program, and if I treat my constant also as a variable, I will have two data flow facts. One is this one, which is U3, and one is this one, which is T4. So that's about the data flow fact. Now, why do I need this? Is the way we define a kill set is we say a kill set is a set of all data flow facts which the current assignment potentially invalidates. So we look at this statement, the first one. We know that what it will invalidate is any copy that copies t, because t is recomputed. So if I had some variable, say w, that was equals t before, after I do the statement, I can no longer say that w is t, because I just changed t and I didn't change w. So what I'm going to kill is all copies which are copies of t. And how do I do this? Well, I look at all of my data flow facts. Here I have one. For each data flow fact, I look up what is it a copy of. And if it's a copy of this variable, then that goes into kill set. So here then, the kill set is U3. Because of this. Here the kill set is empty. Why? Because we're assigning A and we have no copies with A. Nowhere do we say something equals A, so it's empty. Here, this is empty because we have no copies with u. We don't ever say something equals u. And this is empty. We never say something equals b. Does that answer your question? Um, yeah, like, so if we do kill sets here, let's do it for this example, just so that we could see what they are. So what are the kill sets? So we have two data flow facts, as we said, U3 and E4. So here we kill anything that has T on the right-hand side, which is this. So the kill set here is U3. Here we kill anything with A, that's an empty set. Here we kill anything with U, that's an empty set. Here we kill anything with T on the right-hand side. So this would be that we kill U3 again. And here we have an empty set because that's it. We don't kill anything. Right? So we have two copies, this one and this one. An assignment to T will kill this copy, and no assignment will kill this copy. Right? Because T always equals to 7, so anywhere we use T from this point, we can plug in 7. So 7 is 7, it never changes. Aha, so there's a question again. So I spent a lot of time in the beginning of this lecture. So if you missed that part, go back and listen to it again. But I'm gonna reply to it. So the question is, why when we look at the kill sets, why do we care about, for example, here? Why do we go and look back up when obviously whenever we assign T here, it will have no effect on other things? Or maybe here, like if we look at T here, why do we look down at this? Because this assignment will happen later. And then it's not useful to know that we cannot use this U at 3 when we do this, because it won't even happen before line 1 is executed. And the answer is that the way we set everything up is we imagine all possible data flow fact that we have, and we just mechanically specify what data flow fact, if it happens to come to this point, which of the data flow facts get killed, which of them get generated. We don't worry about how those statements are connected to one another. We look at each of the statement individually outside of its program. The data flow equations will then put the statements together in the order. And if you look at how we're solving equations, that solving process is what tells us, ooh, this is first, this is second, this is third. But how we set up equations is just based on individual statements. And where this is going to help us is that once we look at programs which are more complicated, programs that have loops, we'll see that actually because we set it up this way without looking at the actual program, but just individual statements, we capture everything we need about the statement in all of its possible context, whether it happens to be in a loop, or whether it happens to be in a straight line code, or whether it happens to be part of a branch, or any of those things. And we don't have to worry about whether the facts that we compute are sufficient for a given context. We just compute all things that the statement can do. Okay. So in particular, if you are worrying about U3, you'll see it next time. But if we have a loop in here, then U3 can flow back up, and then it has to be killed so that we don't end up using the wrong version of it. Now there's another question. So let me erase, leave this here and try and see if I can understand the question. So it says if we have U equals T, and then we also have D equals U, then what would be, do we include D in the same kill set? I'm not sure what that means, but let's get a new page and just do this example. How do I create a new page? Sure. So the example here is, what if we have multiple things? So we have u equals e, line 1. And then line 2, we have d equals u. So what are our data flow factors? So we have 2 copies. Okay, so actually, since I'm doing an example, it's suggested that I add more things to it. E is x plus y. E is x plus y, u is t, d is u. Okay, so what are our data flow factors? We have u at 1, that's a copy of t, and we have d at 2, that's a copy of u. And so we have our, I didn't think. Nope. Oh, this, I see. It's not a program I'm thinking I'm using. It's a different one. Okay, that's why I'm a bit lost. Here we go. So let's look at our gen sets and our kill sets. Okay, so we can generate U1 and D2, and so this is easy. This generates nothing. This generates U1, and this generates D2. Now about the kill sets. So line 0, it kills anything that contains T in it. So when we do this, if I know U1, then I'm gonna kill it. And nothing else has T on it, so that's it. The second statement kills anything that has U in it, so it kills D2. And the third statement kills nothing. Does that answer your question? Yep. So the key thing about this is to really, you need intuition, especially for simple things like you know, it's just like any other problem that you solve with math. If you just have math, you just have equations, and you don't have intuition, then you can easily make mistakes and will not find them until a very long time, and then be surprised why your result is wrong. So you absolutely need intuition. And then you need to be able to separate, when you're solving it, to separate your intuition from the mechanics of the solution. It's just like solving equations in high school or middle school. Um, you have to follow the mechanics in order to ensure that you get the right answer. But you need to have intuition so that you kind of understand what's going on, and you could spot things that look completely out of turn. And it's important to separate the two. Once you start solving it, oh, I just follow those equations and they'll give me an answer, and not worry about all of the things that sort of intuition gets in the way, where things become less than intuitive, when examples become a little bit more complicated. Okay, so we have copy propagation. Okay, so this is here. Now, one question that I was expecting, but nobody asked is, well, how do I know what is use, right? Because use has to tell me which variable from which line is used by a given statement. Right? And that we can also compute by a different data flow analysis, just by looking at which variables flow where. So kind of like available expressions. Okay, so the last one is we want to do dead store elimination. So if you remember from our overall picture, we did copy propagation. Again, let me erase this here. So our copy propagation would replace this by t. And now we need to do some kind of analysis to figure out that, oh, actually, line 3 is no longer needed. And what we want to do, and the way to eliminate it is the dead store elimination. And in order to do that store elimination, we're going to do reaching definitions, and we're going to keep all definitions, all assignments like this. If their left-hand side is used somewhere, so it reaches something, some use, and then we're going to eliminate all the ones which are computed but not used. Okay. Again, so let's see. What do we have in terms of our equations? So ints are constructed from outs. We have Jan, Keel, and in. Right? So this is kind of the same, except what's different. Oh, no, but there is a difference here. Right. So the difference is in the collecting operator. So now when we say if I have multiple predecessors and I have them was flowing into here, then I want to say that a definition is reaching this node if it's reaching it either from here or here. So my combination operator is an or a union rather than an intersection or a conjunction. This will not be a big issue right now because remember, we're doing straight line code. If we have straight line code, whether we take a union or intersection of a single input, it's the same thing, in equals out. The rest of it is the same, right? We kill, first remove things that should not be there, and then we add things which are new. The set of data flow facts is different. The set of data flow facts will be the set of variable definitions. So in is the variable definitions that get to the beginning of a statement, out, the set of variable definitions that go out, gen is a set of definitions that are generated, and kill is a variable definition that's killed by a computation. So let's look at our analysis. So for reaching definitions, we have a disjunction or an or a union. For available expression, we had an conjunction or intersection. So that's our so-called confluence operator. And so the difference here is really a must versus may analysis, where available expression tells us something is available no matter how you got to a statement. A reaching definition says there is some way you can get to a statement where the definition reaches you. Won't really be a big difference until we get to programs where there are different executions. Here we only have straight line code, so we'll get back to that. Okay, so what do we do here? So data flow facts, again, it's variables being defined. Because the same variable can be defined multiple times, we separate them by line numbers. So again, we're going to have E1, A2, U3, and B4. Okay. And then a kill set is any other definition of a variable with the same name, but a different line number. And we set our computation. So what is our so in order to do this, something has to be in here, and we imagine that what came in is all the variables which are used but are not defined inside this program, because this is a program snippet. So we assume that there's some implicit statement at line 0 that defines x0, y0, and z0. So this is what is reaching there. And then each successive statement generates exactly the variable it defines. So in this case, right? A1, A2, U3, B4. Kill sets are empty because there's no variable that is assigned multiple times. So that's easy. But let's look at this example where a variable is reassigned multiple times. Let's do this. Let's do this computation here. So our data flow facts here will be x0, y0, z0, e1, a2, u3, u4, b5. Right? Now, this is the important part, that we have two u's. And so when we look at our gen set here will be e1, a2, u3, u4, b5. And the kill sets, that's the interesting part. Empty, empty. Here, because there are two assignments to u, whenever we create one, which is u3, we have to kill all the others. So what we're going to kill is u4. And here, because again, there's two of u's, we're going to kill u3, which is the other one. And then here, it's nothing. And again, we don't look at the order in which the statements appear. We just look at a statement and we say, okay, let's pick, say, this one. And this statement, we say, oh, it's assigning to u, which means it will kill all facts about other versions of the u variable. Oh, here's another version of the u variable. That's the one that we're going to kill. Okay. Even so, in this particular execution, if we go from top to bottom, the assignment at line 3 does not actually affect an assignment of line 4, but the gen and kill sets are flow insensitive. They don't care about the context of the statement, just about what the statement is doing and what are other data flow facts available. Okay, back to our previous previous computation. So our equations are now slightly different because we have an or in here instead of an intersection. Of course, our program is straight line, so it's still going to be the same equations because a union of a set containing one predecessor is the same as intersection of that one set. And so we get the following equations. So we said that we envision some kind of statement 0 that outputs definitions for the variables which are not in this code snippet. So in1 is not empty as before, but it's rather x0, y0, z0. And then the rest is the same. Inf2 is in2 is out of 1, in3 is out of 2, in4 is out of 3. The equation says the same as before. Again, we see that we can solve them because we just plug. And every time we plug, simplify, we get a new set, a new variable is solved. We keep solving it. Our gen sets and kill sets, as we've computed them, we plug them in, we do the solution, we get this. Okay? So we'll say that, so what does it mean? It means that, well, initially, in order to run this program, we assume that x0, y0, and z0 are available. And then at inf2, at this point, we now also have t1. And at this point, we also now have a2. And at this point, at inf4, we also now have u3. So this is definitions that go to this place. Right? And then at the end of the day, an out at here, we also have b4. So now, once we have reaching definition analysis, we can do the that store elimination. We're basically going to look at whether there is a definition that reaches that's available, that reaches things, but it's never used in any expression. So for every expression, we compute the intersection of what goes in, so what definition reach it, and what it is using. Right. So we'll see that the first statement uses x and y, the next one uses t and z, the next one uses t, and the next one uses t1 and z. And so we know what definitions of stores are alive, meaning that they're actually both created and used, which is anything that appears in here. And then whatever is not in there is not used, is dead. So for example, well, we just look at what's available. So we have B4, so that's not used. We have A2, that's not used. And we have U3, that's not used. Okay. So we know that all of those can be eliminated. Now, of course, this is just a snippet, so we have to be careful. So if we have a snippet and we have variables that are not used by the snippet, we need to know whether they're local or whether they're used somewhere else, potentially. If, for example, we expect that at the end of this computation, we do something like return a comma b, then a and b are actually used. They would be used by the statement later on, and u would be the only one that we can eliminate. Yep. So again, pausing for questions. That I think more or less have maybe one more summary slide to go through. Right. So there is a question about use. So use, I'm using use here informally because it can be easily computed. I'll answer the question in a second. I just want to see if there's any more questions. Okay, so don't see any more questions. So I need to insert another page and do an example. So the example is like this. Right. So 1 is e equals 2, u equals e, 3, e equals 2, 4, 5, e equals 2. And then the question is, what would be the use of rating? Okay. So for use, I need to, I can't just say a variable. I have to say variable and a line number because there's multiple assignments to the same variable. The use here will be x0, y0 with any snippet of code. If it has some variables which are not defined in the code, I'm assuming that they are in fact defined somewhere else, and it's not a program that they cannot be compiled, that is syntactically not well founded. So here we use e at line 1. Here we use u at line 2 and y at 0. Here we don't use anything. 7 is not a variable. Or we can say that we use 7 if we want to use 7 also as a variable. And here we use u at line 4. So so at line 5, we're using the one at 4. We're not using the one at 2. That's right. And again, it can be like to compute the set of users, you have to formulate it also as a data flow problem. And so we know that we need to look at what was the latest definition of each variable. And so we know, for example, that this line 4, that new definition kills the previous definition. And because it kills the previous definition and creates a new one, which is 4, the only one that gets to here is 4. Okay, so that's all that we have for today. So we went over this pipeline. Do go over the slides again before Monday. So what we're gonna do on Monday is the same thing, but we're then gonna introduce loops and branches in our programs. And really, not much will change. So the figuring out what kind of equations we need for a data flow analysis, whether it's the confluences, intersection, a union, whether it's forward or backward, it's exactly the same straight line code and node. The only difference will be is how do we solve those equations. We'll see that we solve them by a fixed point computation. Essentially, whenever we have some kind of recursive dependency, circular dependency in the equations, we're gonna plug something as a solution for one variable to break the cycle, solve it, and then compute a solution for the variable again, and keep doing this repeatedly until we get to a fixed point. But other than that, that's it. And if you think intuitively, any of those things like available expressions or copy propagations, you'll see that, well, if you get into a loop, you simply take your data flow facts and you move them from an end of a loop to the beginning of a loop. Because the number of data flow facts is finite, and because everything is monotone, whenever we do computation, if we have more facts, they don't disappear. They keep just accumulating, and the set of available facts gets bigger and bigger and bigger. And it means that eventually our fixed point will always terminate. But we're going to do all of this on Monday. The focus on Monday will be very much on understanding how those equations are solved and less on the definitions of the equation itself. So that's why you should really be up to speed with a gen and a kill set and be able to easily compute them for all of those examples. That's it. I think it was a little bit shorter, but that was expected because our Monday lecture was a little bit longer. If you have questions, ask them on CampusWire. Lab 11 is out. Lab 12 is also on the skeleton, so you could start doing that one as well. Lab 11, I didn't get a chance to merge it into master last night, but I did merge it into master this morning. If you're waiting for this, call out. Good luck. That's it. I'll see you Monday.